Welcome back to Neural Intel. Today we're diving deep into a really fascinating area where artificial intelligence meets the fundamental science of partial differential equations, PDEs.
Right, PDEs, they're basically the math language we use for describing how stuff changes in the physical world. Think like heat moving through metal or how fluids flow.
Exactly, and solving them is just, absolutely critical in tons of science and engineering fields.
It really is. But, traditionally, solving PDEs meant using these super complex numerical methods. You needed a lot of specific expertise, serious computing power.
Or, more recently, neural networks have jumped in. But they often need huge amounts of data, and sometimes you don't really know how they're getting the answer. They can be a bit of a black box.
Which brings us to today's paper, CodePDE, an inference framework for LLM-driven PDE solver generation. It's proposing something pretty different.
Yeah, using large language models, the kind of AI behind things like ChatGPT, to actually automatically generate the computer code needed to solve these equations.
It's a really interesting core idea, isn't it? Can you just give an LLM a description of the PDE problem?
Like the equations, the condition.
Right, and have it just write a working program, a program that's accurate, maybe even efficient.
Seems like a big ask. But that's what we're digging into today, this CodePDE framework.
Exactly. We want to unpack how it works, leveraging the LLM's ability to reason, to debug, even refine its own code, all without needing, specific training data for every single PDE problem.
Okay, so let's really get into the framework itself. The paper basically treats PDE solving as a code generation task for these LLMs.
That's the core framing. And it's key that CodePDE is an inference framework.
Meaning?
Meaning it's about cleverly using already trained LLMs for this job. They're not training new models from the ground up specifically for PDEs. It's about the prompting and the workflow around the existing LLM.
Got it. And the paper outlines 5 main steps, right? Figure 2 shows them. Let's walk through. First up, task specification.
Okay, task specification. This is step 1. You take the whole PDE problem, the governing equations, the physical domain, the boundary conditions, initial states, all that math stuff.
And translate it.
Exactly. You translate it into a natural language description that the LLM can actually process and understand. The paper gives an example for Burger's equation, showing how you describe it.
So, making the math problem LLM-friendly. That's step 2, code generation. How does that work?
This is where you prompt the LLM. You ask it to generate the actual Python solver code. They specify a particular function structure, a signature, so the outputs are consistent and easier to evaluate later.
And they use that chain of thought prompting here.
Right, chain of thought. It's like giving the LLM hints, guiding it through the logical steps needed for complex numerical algorithms. Appendix B.1 has the prompt details if you really want to see the specifics.
Okay, so the LLM spits out some code, but I guess it's not always perfect first time. Which leads to step 3, debugging.
Exactly. Perfect code first try is rare. So the debugging step is automated. They run the generated code. If it crashes, if there's an error.
It happens.
Oh, yeah. The error message gets fed straight back to the LLM.
Okay.
And the LLM is prompted to revise the code to fix the bug based on that specific error. It's an iterative loop.
A self-debugging loop. How effective is that?
Surprisingly effective. The paper says it boosts the rate of bug-free runnable code from about 42% initially to 86% after debugging. It's a huge improvement.
Wow. Okay. That self-correction is powerful. So once you have code that runs, step 4 is evaluation. How do they know if it's any good?
Evaluation involves running these working solvers and comparing their output, their predictions, against very accurate reference solutions.
How do they compare?
Mainly using a metric called NRMSE, normalized root means squared error. Basically, it measures how far off the LLM solution is from the true one. Lower NRMSE means better accuracy.
Makes sense. Anything else?
Yeah, they also do convergence tests. Does the solution get better if you use a finer simulation grid? And they measure execution time. How fast does the code actually run?
So accuracy, convergence, speed. The key things you'd want in the solver. Then the final step, solver refinement.
Right. In solver refinement, they take the evaluation results, specifically that NRMSE accuracy score, and feed it back to the LLM again.
So telling it how well it did.
Exactly. And then they ask it to analyze that performance and try to generate an improved version of the solver. It's like a feedback loop for optimization, aiming for better accuracy.
It's a really neat cycle. Generate, test, debug, evaluate, refine. So what are the big capabilities this CodePDE framework seems to unlock?
Well, several key things. First is reasoning. The LLMs aren't just copying code snippets. They seem able to explore different ways to solve the PDE.
Like different numerical methods.
Yeah, exactly. Finite difference, finite volume, spectral methods, and different ways to handle the time evolution. Explicit Euler, Runge-Kutta, even more complex IMEX schemes. So they can generate a diverse set of strategies.
That sounds more sophisticated than just pattern matching. And then there's the debugging we talked about.
Definitely. That ability to autonomously find and fix errors based on runtime feedback is huge. We saw the numbers that jump to 86% bug-free code is really significant. Figure 3 shows this clearly.
And the third one, refinement, using that performance feedback.
Absolutely. The way the solution quality consistently improves across different PDEs when they apply this self-refinement loop based on the accuracy feedback is really compelling. Table 1 shows refinement often pushes the performance up quite a bit.
Okay, and the last capability mentioned is test time scaling. What's that about?
Test time scaling is about getting better results by basically trying harder during the inference phase when you're using the LLM. They use a best event approach.
Meaning they generate multiple solvers?
Exactly. Generate, say, in different solver codes, evaluate them all, and then pick the best performing one. Figure 4 suggests there's a scaling effect. The more samples you take, the better the best one is likely to be, though you hit diminishing returns eventually.
So try a few options, pick the winner. Smart. Now, the big question. How well does CodePDE actually perform compared to, existing methods or human experts?
The benchmarks are pretty interesting. Table 1 and Figure 1 lay it out. On average, across the 5 PDE types they tested, Advection, Burgers, Compressible Navier-Stokes, CNS, Darcy Flow, and Reaction-Diffusion CodePDE gets close to human expert performance.
Close, or better.
Well, here's the kicker. For 4 out of those 5 PD families, CodePDE actually surpassed the quality of the solvers written by human experts based on that NRMSE metric.
4 out of 5, wow, that's quite something. Any specific standout examples?
Yeah, they highlight the Burgers equation. The Gemini 2.0 Flash model, after refinement, got a significantly lower NRMSE, meaning much better accuracy than the human expert solver. Figure 1 really visualizes this. You can see those bars for CodePDE, with refinement often reaching higher than the human baseline.
That's genuinely impressive. But it wasn't perfect across the board, was it? You mentioned 5 families.
That's right. The 5th one, the Reaction-Diffusion equation, proved tougher. For that specific type of PDE, the LLM-generated solvers didn't perform as well as the human expert.
So still some challenges depending on the problem type.
Huh?
How does it stack up against other AI approaches for PDEs?
Table 2 gives a comparison. They look at traditional methods like finite difference, but also other neural PDE solvers, things like FNO, UNet, PENs, and also these newer agentic workflows like FunSearch or AID.
Yeah.
CodePDE holds its own, showing competitive performance. And interestingly, its overall design might be a bit simpler than some of those agentic approaches, which can involve quite complex search strategies themselves.
Simplicity can definitely be an advantage. Okay, let's look a bit closer at the solvers themselves. What did the analysis show about that debugging step's effectiveness?
Figures 3 and 10 really drive home how well the self-debugging works. As we said, it dramatically increases the bug-free rate for various LLMs and PDEs. The top models, Gemini 2.5 Pro, Claude 3.7 Sonnet, DeepSeek R1, GPT 4.1 O3, they're getting over 90% bug-free rates after debugging.
That's really reliable. Does it take many tries to debug?
It varies. Depends on the LLM and how tricky the PDE is. More complex problems might need a few more rounds of that run error fix cycle. Makes sense, really.
Yeah, it does. What about the gains from self-refinement, getting that accuracy feedback?
The refinement step provides pretty substantial accuracy boost. Table 1 shows this clearly, often pushing the LLM solvers past the human expert level. An interesting little finding was that the models best at the initial code generation weren't always the best at refinement. Yeah, like Gemini 2.0 Flash, maybe not the top generator initially, showed really strong improvement during refinement.
It suggests different models might have different strengths. Initial creativity versus iterative improvement. What about that test time compute idea, generating multiple solutions?
Right, the best of ensembling. Figures 4 and 13 show that generally, generating and evaluating more solutions improves the quality of the best one you find.
But it levels off.
Yeah, you get diminishing returns. You might generate 16 solutions, and the best is much better than generating just one, but the jump from 16 to 32 might be smaller. The key point is that combining good initial reasoning, this sampling, and then refinement is way more effective than just a single shot.
It's a multi-pronged approach. Okay, what about the code itself? Its quality, efficiency. How fast did these solutions converge?
Figure 5 looked at convergence rates, how quickly the error drops as you refine the simulation grid. Most LLMs tended to generate first-order methods.
Okay.
Simpler, but often need finer grids, more computation for high accuracy. However, some models, like QWQ Plus and O3, did occasionally manage to generate higher-order schemes, which can be more efficient. Appendix Figure 11 has the detailed breakdown.
And runtime speed, are they fast?
Figure 6 shows execution times vary quite a bit between LLMs. Gemini 2.5 Pro seem to generate faster code on average, but they do note LLMs can sometimes be inefficient, redundant calculations, non-optimal loops, things like that.
Room for improvement there, perhaps? And CNS equations were slower.
Yeah, the compressible Navier-Stokes solvers tended to run slower, which isn't too surprising given the physics they model are inherently complex. Appendix Figure 14 has all the specific timings.
Got it. Now, one thing that seems really valuable is the interpretability. You can actually look at the code the LLM wrote, unlike some neural net approaches. What did they learn from doing that?
That's a huge plus, yeah. Figure 7, 8, and 9 give some great insights by looking under the hood. For Berger's equation, they analyze the numerical schemes, finite difference, finite volume, etc., and the time-stepping methods, Euler, Runge, CUDA.
What did they find?
Most LLMs preferred simpler schemes, like basic finite difference and explicit Euler. Figure 9 looked at the Python libraries, used PyTorch, JAX, SciPy, NumPy. Different models prefer different libraries, which could affect speed.
And it helped explain failures too, right? Like with the reaction-diffusion equation.
Exactly. That was a key insight. By looking at the code for the reaction-diffusion solvers, they saw that LLMs usually used finite difference for the reaction part. Human experts, however, often handle that reaction term differently, sometimes using an exact analytical solution for that specific part.
Ah, so understanding the code helped pinpoint why it wasn't performing as well. That's really valuable.
Definitely. It shows the limitation wasn't just random, but tied to a specific algorithmic choice the LLM made.
Okay, so let's try and wrap our heads around what this all means. CodePDE seems like a genuinely significant step, using LLMs for complex scientific computing, specifically PDEs.
I think so, yeah. The ability for these models to not just write code, but to debug and refine it based on performance, often hitting or beating human expert levels, that's pretty remarkable.
It really opens doors for automating parts of the scientific process, maybe speeding up discovery or design.
And that interpretability factor is key. Being able to look at the code, understand the method, diagnose issues, that's a big advantage over black box AI solvers.
Absolutely. This deep dive really paints a picture of a future where AI is this powerful, transparent assistant for mathematical modeling and scientific computing. It could potentially make these advanced techniques accessible to more people.
It's an exciting direction.
But here's where it gets really interesting to think about, right? What are the potential limits here? Can we fully trust LLMs for these critical tasks? Could biases in how they were trained affect the kinds of solutions they generate, or maybe how well they work on certain types of PDEs we haven't tested yet?
That's a crucial point. The training data is vast, but might have blind spots or lean towards certain common methods.
And how do we best combine this AI capability with actual human expertise? We saw the LLM struggled with reaction-diffusion where a human expert knew a better trick. How do we build systems that leverage the best of both, ensuring robustness, reliability?
These are definitely the big questions moving forward as this tech evolves. We need to think carefully about validation, verification, and keeping humans in the loop where their insight is critical.
Absolutely critical questions. The CodePDE paper gives us a fascinating glimpse, but there's clearly a lot more to explore.
For sure, it lays some really interesting groundwork.
We definitely encourage you to check out the paper itself if you want all the technical details. Thanks for joining us on this deep dive into the technical heart of neural intel. And remember, you can find links to the latest AI and ML research papers, including this one, over on our webpage. The link is in the bio.